Why are patterns important in determining drag?
What algebraic relationship shows that a car has drag?
Explain the relationship between pressure and glow.
This is one of NASA Langley's many wind tunnels. It's called the Basic Aerodynamics Research Tunnel, or BART for short. Engineers like me use the BART in a technique called flow visualization to try to understand how the air flows around aircraft. By looking at or visualizing the airflow, we can help aircraft designers create new shapes that are more aerodynamic and produce less drag. Drag slows down a vehicle or an object, as you observed in the activity you just conducted. Recently, NASA Langley used its experience in testing and simulating aircraft to help a car manufacturer visualize and describe the airflow over one of its automobiles. What we as engineers would really like to see is the air flowing continuously from the front of the car to the back of the car, like the flow over this cylinder. There is no interruption in the airflow and there is no drag. Unfortunately, this is not how things work in real life, so we have to make airplanes and cars streamlined. This particular automobile is streamlined, which means it was designed to offer minimal resistance to airflow. Because of its shape, this car has little drag.
You know, that sounds like our activity. The tetrahedron had the lowest drag because of its shape.
That's right. The shape of airplanes and cars is mainly determined by aerodynamics and safety. However, a car has additional factors that may affect its shape. The vehicle must look good for people to buy it, the passengers must be comfortable, and the vehicle must be able to transport people, cargo, or both. With this in mind, automotive engineers use geometry to design cars with one of three shapes: a hatchback, a squareback, or a notchback. Which of the three shapes do you think would have the highest drag?
Looks like the notchback has the most drag.
You're right. After deciding on the shape to test, we created a scale model of a typical passenger vehicle with a notchback design. To visualize and measure the airflow around this model, we used the BART and materials like kerosene and titanium dioxide, a white powdery substance used in paint. Visualizing the airflow provides a picture of how the air moves around the vehicle.
Okay, so how do you visualize airflow? You can't really see air, can you?
No, you can't, and that's a good question. Without special materials, you really can't see air flowing. So we mixed titanium dioxide and kerosene together and applied it to the surface of the model. We turned on the wind tunnel, and as air flowed over the model, the kerosene evaporated or turned into a gas. The titanium dioxide left on the surface shows us an airflow pattern. This pattern tells us how the air is moving close to the surface. The measurements we collect allow us to describe the air's properties and motion with numbers.
Luther, that looks really cool, you know, but what does this pattern say about the shape of the car and the drag it produces?
Well, this pattern tells us that the air is actually traveling in the same direction as the car, or in other words, towards the back window. This is called reverse flow. Reverse flow creates low pressures on the back of the vehicle, which increases drag. Remember this drawing? See how the air flows smoothly over the cylinder and comes together again in the back? Although this isn't how things work in the real world, the air pressure in the front, PF, is the same or equal to the pressure in the back, PB. When the pressure in the front is equal to the pressure in the back, then there is no drag. However, look at our notchback model. See how the air flow separates at the back of the vehicle and the air actually begins to flow in the reverse direction? This is reverse flow, and the pressure in the front of the model is greater than the pressure in the back. When the pressure in the front is greater than the pressure in the back, you have drag. Flow visualization helps us understand how the air flows over the model, but in order to measure the pressures on the surface, we had to use additional techniques. The most exciting is probably pressure-sensitive paint. In addition to NASA Langley, NASA Glenn Research Center in Ohio, and NASA Ames Research Center in California used pressure-sensitive paint in their wind tunnel tests. Pressure-sensitive paint, or PSP, is a special paint that glows when exposed to blue light. The glow is really due to special molecules embedded in the paint called luminophores.
Luminophores. Sounds like a word that comes from illuminate?
That's right. These luminophores are excited or given excess energy by the blue light. The luminophores don't like to have excess energy, so they get rid of it by either glowing or by bumping into nearby oxygen molecules. The behavior of the luminophores allows us to see a relationship between the brightness of their glow and the pressure on the surface.
A relationship. Sounds like algebra.
That's right. I use algebra in my work every day. Let me show you. Remember when I said that the behavior of the luminophores allows us to relate the brightness of the glow to the pressure on the surface? This is done using a graph like this. The curve on the graph shows an inverse relationship between pressure and glow. When glow increases, we know the pressure has decreased. But when glow decreases, we know the pressure has increased. This inverse relationship can be represented with the following algebraic equation. Pressure equals quantity glow minus 1 divided by the slope of the curve. Using the graph in this algebraic equation, we solve for pressure. The pressures we calculate can be displayed using different colors like this. The red regions show where the pressures are high, and the blue regions show where the pressures are low. As you can see, the pressures in the front of the car are higher than the pressures in the back. As we calculated earlier, this difference determines the vehicle's drag. This information is used by car designers to decide if the shape or geometry of a car needs to be changed.
If I were a car designer, I'd change the notchback shape on the car. It creates too much drag.
Well, Van, the research conducted here at the NASA Langley Research Center will be used by automotive engineers and designers to create new designs and shapes with reduced drag and better fuel efficiency. This allows drivers like us to save money and protect the environment.
Okay, we've seen how different shapes affect drag. Now, let's head back to First Flight Middle School and see what would happen if we changed the frontal surface area of an object. Are you ready, guys?